And one more problem. We have two machines here. We are applying the input voltage 230 volt 50 hertz. They are similar machines. And we have the power output from the machine is 500 watts. This machine is also the same. We are applying the same input. We have the machine 1 and machine 2. So input is 230 volt 50 hertz and power output is 500 watts. Two machines are having the same power output. But the power factor of this machine is 0.8 and power factor of this machine is 0.9. Or you can use any other value you can just for the checking. So now the question is, okay, first both machines have the same power output capacity. Both machines require same input voltage and frequency, right? Same input, same output. Then, but power factor is different. Here we have the 0.8 and here we have 0.9. Because of this, what will happen? Let's see now. Now let us calculate the true power and apparent power for both machines. We know the formula for true power. So the power factor is equal to true power divided by apparent power. It means I am bringing this apparent power to this left side. So AP is equal to TP divided by PF. So TP is 500 watts. That is the true power provided by this machine. 500 divided by the power factor is 0.8. So I will get the apparent power is 625 watts. So I am applying 625 watts, but the machine output is only, this is the capacity I am applying, but the machine is providing only 500 watts true power. Now we have the power factor, because of this power factor 0.8. So the current now we can calculate. Current I is equal to AP by divided by V. This is nothing but the same formula. P is equal to V times I. So here P is just nothing but apparent power AP. So here we are putting the I, we are keeping here, and then we are bringing the V down. So I is equal to AP divided by V. So 625 watts divided by 120 volt, you will get the ampere. The current is 5.2 ampere. Exactly 5.208. That's correct.
That the input should be 230.
It's a 230 volt. Yeah. It's supposed to be 230 volt. So then the calculation will be different. 2.71. 717. Okay, so now we will find the same calculation for this machine, machine 2. So we know the formula. So AP we are finding. So here the AP is, we are using this power divided by power factor. So 555.5. And then now we have to calculate again the I value. So this is 230 volt. This is 2.415 amps. Is it correct now? So now you can see here machine 1 and machine 2. So they are consuming different current. So the machine with a higher power factor is drawing or taking less current from the source. This is 2.4. This is 2.7. Of course, it's not a very big difference, but still some difference when you calculate or when you think from the practical perspective. So the machine is running like 24 hours a day. So it's consuming this 0.3 amps difference. That means like 300 milliamps about. So it means you will pay more bill for the energy consumption. So it means when you choose the machine, or better buy the machine with a higher power factor, or you have to use some kind of power factor correction circuit or external circuit or device connect to this machine. For example, if you use this one, then you have to use the power factor correction. That is going to cost extra money for you. So this is not really a good solution. So it's better to use the machine with a higher power factor. Okay, so same machine, but with a different power factor. The machine with the higher power factor draws less current. That is the conclusion. It means you pay less for energy. So yeah, that's all. You have to choose the power factor as close to 1 as possible. So here some points. Try to remember. These are some bullet points. For purely resistive load, we have power factor as 1. For purely inductive or capacitive loads, we have power factor as 0. That is very worst. And poor power factor can be corrected by adding a capacitor to the circuit. The capacitor will have an opposite amount of the reactive power. That is why the capacitor is helping us to pulling up the current. And also too much capacitance. When you add the capacitor, you cannot add too high values. That will also affect the power factor and also the current consumption. And advantages of good power factor. Of course, you are improving the system efficiency. So you are reducing the power waste or energy loss. If you reduce the energy loss, then it means you are also saving the cost. And also the lifetime of the device is increasing. And of course, like in your home, if you have some machines which has a poor power factor or worst power factor, if the EB or electricity board, if they come to your home and they check, right, every 10 years once or something, randomly they come and they check the house, what kind of loads you are using in your home. If they measure the power factor, if they see some kind of machines and with the worst power factor, if they find out that, then they will put the fine on you. They will ask you to pay money. So penalty. So they do that actually until now. So poor power factor will also make penalties for the user. So we better always, that's why we have to maintain the power factor as good as possible. So if you use the good power factor machine with a good power factor, the penalties can be avoided and also the electricity bill will be reduced. And in the modern technology, there are many methods to measure the power factor even directly. You don't need to make calculations manually. That was the olden days method. So you can use this kind of fluke. It's one of the devices which we can use to measure the power factor. It will show the power factor value. This is the practical way you can measure the power factor. In case if the power factor goes down, you have to immediately improve the power factor by using some methods.